In the first episode of Square Micro Intro Movies, we used the topology optimization to carry out the best design at the first stage of additive manufacturing, regardless of the effect of fabrication process on the part quality. Right after the designing step, we first need to be sure about the quality of the part produced. There are two different approaches for this. One is manual optimization of the part quality, which is done by producing large number of samples by different sets of process parameters that will definitely incur high material expenses on the manufacturer. The more elegant way would be via a proper calibrated numerical model. These numerical models are valuable devices which are capable of predicting the parts quality, which in this way the manufacturers would save a lot of money and time. Since SLM is a process including large heating and cooling rates, it usually results in warpage, deformations, or even defects such as cracks and bowing. For the matter of comparison, it is interesting to know that the laser heat flux during SLM is of order of 1 to 10 gigawatts per square meters, which is about 1 million times more than the sun heat flux we experience every day. Also, it should be noted that SLM process is really quick. There are several software packages that can be used for SLM modeling, like COMSOL, Abacus, and ANSYS, which are based on finite element, and ANSYS Fluent and OpenForm, which are based on finite volume method. COMSOL is a powerful software which can take care of thermomechanical modeling of SLM. In this case, the thermal field is basically the driving force for the mechanical model. In this video, we are going to show you how easily you can implement the COMSOL for thermal modeling of SLM, which is the main cause of deformations and microstructural evolution. Here we use two rectangular blocks, which the first one will receive laser heat flux, then it cools down for 2 seconds. Then the next block will be established, and the laser starts scanning it. In this step, the required material properties are specified, which are mainly heat capacity, conductivity, density, surface emissivity, and latent heat of fusion. COMSOL has a default material library which allows us to choose between nearly a wide range of materials. In this case, we simply choose titanium beta 21S from the library. The next step would be to choose the governing physics. So we choose the heat transfer in solid, which enables us to have the spatio-temporal variation of the temperature field during scanning and cooling cycles. Then we put the boundary condition. Bottom surface is thought to be isolated. The rest of the faces will be exposed to atmosphere and radiation. We impose the laser heat flux on the top surface. Its distribution is Gaussian, where the maximum heat flux happens at the center of laser beam. Making the mesh in any type of numerical modeling is of paramount importance. Basically, in finite element and finite volume, we divide the geometry into a number of cells or elements. Then the software will automatically solve the energy equation on all elements. In our case, to get a good resolution, we go for cubic elements with 100 micrometers size. Here you can see that the laser starts scanning the first layer with a constant speed of 200 millimeters per second. The maximum temperature rises to around 4500 centigrade degrees. After the laser scans the first line, it goes to the other line and moves in opposite direction. After the scanning of the first layer, it cools down for 2 seconds, where the average temperature goes down to around 1000 centigrade degrees. Then the next layer is established, and again the laser starts to scan it. But this time temperature is higher than the first layer, due to heat transfer from previous layer which had already been established.